So in this Snap Circuits video, we are looking at project PC66, the drawing resistors PC, and finishing up with project PC73, the sound mixer PC, which is the last circuit in the book here for the CI-73, and the very last project of the entire Snap Circuits series. So, project PC66 drawing resistors PC is actually going to have us go back to the project 512.692 book that's with the SC750, and we're actually going to be redoing projects 516, 517, 518, and 519, except now we're going to have our computer CI-73 interface cable as part of it, looking at the output on the scope here. So in effect we were actually doing 4 projects in the place of PC66. So this is how project number 516 is in the book, which we have done before back in the original video where it was located. So that's how it looks on our board. We have our oscillator circuit with our C1 capacitor going through a feedback circuit with our NPN transistor, and then we have our little jumper wires connected off of here from a point of our transformer and also from our 100,000 ohm resistor. And when we connect these, we help create a connection, but also when we use the graphite lines, which we're going to be using on the book here, of course those act as resistors, and variable resistors based on the graphite moving around, including of course our own human skin. So one thing I do need to get here is a pair of gloves, because I do remember from the last time this project was done I need to keep myself isolated, otherwise I'm going to actually interfere with the projects. And let me go ahead and get Cam Studio recording here. Let's get our scoop running. Now I'm going to move this up out of the way so that we can see the book here that we're going to be working with. Here, other glove. Now we're ready. So when we turn the circuit on, nothing's obviously going to happen because we have this broken connection right now. But because I'm using my gloves, I'm not making any contact. But if I touch these together, we can hear the tone on there and see it on our scope being reflected there. So now what I'm going to do is take these and place them on our graphite. And I've already tested these, and it's actually still able to conduct, despite being done almost a year ago from the time I looked up the video on this. So just need to get one end touching there and get the other end to touch on the line, so we can hear the output from the speaker and we can see it reflected on our scope there, which I've got set to the 5 milliseconds per division. And if I move these around a little bit, that's about as much as we're going to see on that line. So let me go ahead down one here to this line, get my connection on there, and as I move it around on here, we can of course change the resistance, and by changing the resistance we change how fast or how slow that circuit oscillates. As we see, we don't change the overall power of the circuit because the height of the wave is not going up or down, but we are changing the wavelength there. So, oh, I came off of it. It's a little hard to feel having to wear gloves here. So let's go on to the third line. Get my point there. So bring it closer. And you see this one, there's much less resistance because it's a bigger strip and it's also longer. And then let's go down to the last strip, which is both the longest and the widest. And of course I can move the other end here around on it too. So we get the idea of how that works. I see I'm making a little bit of a mess on the paper. So we move on to the 517 side of that, which is the electronic kazoo. So with this, we have a wide line that gets narrower and narrower, and then it's kind of just a simple, straight little strip here. And we'll see how that produces a waveform on our circuit. So that we find that point and just hold it down. Take out the strip. It gets a little busy here having the book, the circuit, and the computer all together on the bench here. A little hard to hold. Do it that way. Then we have it up to the high end. Of course, it's oscillating nice and fast there. We can see from our waveform. And we start bringing it away on our line. We see it getting slower and slower. And eventually the circuit is ticking. And because it's oscillating so slowly, see, especially by the time we get to here, you can hear the circuit ticking, but it's oscillating so slow that we can't see it on the oscilloscope because the oscilloscope just isn't sampling fast enough for how slow this is going. But start bringing it back the other way. Once I get a connection, then we can start seeing it again. So that's how project PC517 is for that part. So now we're going to look at 518, which is a second version of electronic kazoo. In this we have numbered intervals, and the line gets progressively smaller with each one of these dots filled in between them. So is that showing? There it is. So I'm going to hold this on 1 as best I can, and then we're just basically going to go from 2, 3, 4, 5, 6 all the way down to 11 here. We don't have to drag it, we just place it in the circles. Get that point. So there's our connection at number 2. There's a connection at 3, and you see how the waveform changes between the numbers there. And of course, as we go down, it's going to oscillate slower and slower because we're going to have more and more resistance here. So that one, we're just seeing a pulse there on the oscilloscope. And again, we're at the point where the circuit is ticking, so we're not really going to see anything on the scope at this point. But we can at least still hear it through the speaker. So that's 6, 7. Let's see. Got a bit of a broken connection at 0.8. Yeah, I got a connection at 0.8. But we of course did this project before, and like I say, it just gets slower and slower on the ticking there, and we can't see it on the scope anyway. So that's that. Now project 519 part is the water resistor. So for that, over. Got my glass of water here in the Tom and Jerry cup, which is exactly the same one that I used for project 519 the last time I did this. And we're just going to stick the jumper wires in the water, and the water itself will act as a resistor. And we'll see what it looks like there. Of course, we can vary that resistance by taking the jumper wires out of the water. But you see, there's actually a lot less resistance here than was with the graphite. So I'm actually going to change the scale of our scope to a 0.5 millisecond per division. And that lets us see that a little more clearly. Don't even need my gloves for this. And as I said, we can vary that resistance by just taking the probe out. Or the jumper wire in this case, I should say. And see, the water itself is pretty continuous. It's not changing the distance I bring it inside there, just to the surface. So that's how Project 519 works, and of course that's how Project PC66 works. And as I said in the original project here with the water, you can add salt to this, and salt will make it into a brine, and that will actually decrease its resistance and make it oscillate even faster. So that's one way you can experiment with how salt increases, or I should say decreases, water's resistance. So we're going to move on now to project. Get the right book here. Move on to project PC67, which is the electronic noisemaker PC. So here we are at project PC67, the electronic noisemaker PC. And there it is in the book, and here it is on our board. So we've modified the original circuit a little bit by putting our variable resistor there with our 10,000 ohm resistor, along with putting our press switch controlling our C2 capacitor in parallel with our C1, which is similar to a circuit we did a little while ago, another PC circuit. This one slightly different. So let's go ahead and get the studio recording. And we've got it set to our 0.5 millisecond per division. So when I turn this on, we can see our waveform there when I've got this set all the way to the right. Now as I move this to the left, you see our waveform changes rather drastically compared to what it is here. It starts to go pretty far down, and it continues that way even off the scale until it gets to a point where we just don't get the oscillation anymore. I can bring it back up, and then it goes that way. Let's see what that actually looks like on our 5 millisecond per division scale. You see how different that looks. Now if I put the press switch on, you see with the press switch now the frequency or tone of the circuit has gotten a lot lower, because now we've put this C2 capacitor in parallel with C1. Let's look back at our 0.5 millisecond per division. And you can see the waveform is also, again, a fair bit different from like it is there. And we bring this to the left. Of course, we increase that frequency, but we sort of keep that odd waveform. Let's see, what does this look like on FFT side? So we do the FFT scale. You can see how it affects that. Now let's take the capacitor out. Again, you see the difference there on our scope. So that's how Project PC67 works now with Project PC68. Of course, I should have mentioned too, also you could change this capacitor out for the 10 microfarad capacitor here, and that would really limit the frequency or tone on the circuit to where it's kind of just ticking and stuff. But anyway, you could do that if you choose to. But anyway, Project PC68 we're going to take our 10,000 ohm resistor out and replace it with our 100,000 ohm resistor. And as we know from the previous projects, when you increase the resistance, you lower the tone or frequency of the circuit. So we turn it on now. We can see from both our scope and from how the speaker sounds that we have a lower frequency circuit here generating a lower tone. And see, we don't actually cut off this time when we bring the variable resistor all the way to the left, even though we increase the frequency there some, as we can see from our scope. And of course, if we bring our C2 capacitor back in, and the circuit, of course, oscillates even slower than previously. In fact, on a half millisecond per division, we can't even get the second part of the waveform to show, because it's oscillating so slowly. So let's go to 5 milliseconds. So let's look at our FFT scale again. And of course, that's very different from when the 10,000 ohm resistor was there. So that's how project PC68 works. Now we're going to look on project PC69, which is the Bee PC. So here we have project PC69, the Bee PC. Here it is in the book, and here's on the board. So we've modified our circuit a little bit again. At this time we've got, again, our little oscillating circuit with our C1 capacitor, our NPN transistor help doing the switching, all going to our transformer, now putting to our speaker. But in this case we have our press switch, and then we have our capacitor here at 100 microfarad. And what happens is when we press this press switch, we discharge this capacitor, and when we allow current to also flow through the circuit unimpeded, when we let this press switch off, it then starts flowing through the capacitor, which is completely discharged. And then as the capacitor is charging up, as current is going through the circuit, we'll notice the circuit get quieter and quieter till it goes completely out, because again, as this capacitor is charging, the resistance goes up. So as the capacitor charges, its resistance goes up because less and less current can get through it until it's completely charged, and then no current goes through it at all. So let's go ahead and get Cam Studio going. So we got our scoop there. So I press the press switch. We can see our waveform there, and we can hear our tone coming out of our speaker there. You can see the various peaks on our waveform there. And again, the circuit is being kept alive as long as I'm holding down the press switch, and when I release it, you hear the circuit wind down, and you can see it on the waveform as well, that the frequency of the circuit doesn't change, but the power output of it does, again because less and less current is able to go through the circuit as this capacitor ends up charging up. And so no change in frequency, but we lose power in the circuit again because of the charging of that capacitor. And of course we can modify this circuit as we've seen in previous ones. So for instance, if we wanted to, we could take our C5 capacitor and put it in parallel with our 100 microfarad to give us 570 microfarads of capacitor there. And as you would think, when we add more capacitance, the circuit stays active for a longer period of time as it charges both these capacitors up. And so with more capacitance, it takes longer to charge, therefore the circuit actually stays active longer. So that affects the power or current in the circuit, but it's not affecting the frequency or tone that's being generated. If we wanted to do that, then we would add capacitance in another location, specifically up here with our C1 capacitor, whether replacing it or adding it in parallel. So we can do that here. With our C2 capacitor, if I put it across our R5, we'll put this in parallel with C1. And we can see from our waveform there and from the sound of it that we've decreased the frequency and the tone of the circuit. And we can do this to an even greater effect with a higher capacitance like the 10 microfarad. Because you see now the circuit is just ticking. And we can sort of get those pulses on our oscilloscope here. And as I said as before, the circuit slows down because of the charging of these capacitors, but this is changing the frequency. Of course, we can do that here as well. So that's how Project 69 works. Now Project 70, we're going to take the speaker out of it. So I'll just disconnect that one end. And we're going to put our whistle chip across these points of the transformer. And we'll monitor both the audio and waveforms coming from the whistle chip. So this time we put the circuit back to the way it is. We'll press a press switch. And our whistle chip is fairly loud there. I've got to lower the scale down because we've got so much more power or current being shown on our whistle chip there. And you see we're getting kind of the square ends on here because we're kind of maxing out the input on the computer. And you can see it looks a little different on there as the power dissipates over time on this circuit with the difference with the whistle chip there. And again, as before, we can affect both the duration of the circuit and also the frequency. So again, just like before, if we put our 470 microfarad capacitor there, again, the circuit has a longer duration with more capacitance there. You can look at it on this film. Now the case in this, because the whistle chip has some capacitance, we actually do see the frequency change as it loses power, as opposed to just the speaker. And of course, as I say, we can still use capacitors to change the frequency as well. Like if we put our C2 there, and we can see the frequency actually dropping down as it's losing power. And then we can make this really effective here. Or again, we get that pulsing with this 10 microfarad capacitor. Almost sounds like the Wheel of Fortune wheel after it's spinning down. So that is how Project PC70 works, and now we're going to move on to Project PC71, which is the Space War Alarm Combo PC. So here we are with Project PC71, the Space War Alarm Combo PC. There it is in our book, and here it is on our board. So we are taking our alarm IC and Space War ICs and putting them together and outputting to our speaker and also our 2.5 3-volt lamp, which helps pull some power off the speaker there, which reduces the volume. So our alarm IC is being fed, and its output is then being combined with the output here of the space-4 IC, which is being controlled via our press switch, and our photoresistor there to change the output sounds of the space-4 IC. And as I say, they're both being combined together, which is going out to our speaker and our 2.5 3-volt lamp, and then we'll see it on the waveform on the computer. So let's get the scope going. Show you that. And we power on our circuit, and I got my 0.5 millisecond per division scale here. You can see the waveform changing as the alarm IC siren plays, but also while our space-4 IC bomb sound gets overlaid with it. And I can change the sound there, the space-4 IC, and you can kind of see it effect there with the machine gun effect. Camera space-4. Of course, I can turn it off completely, and you can just see the alarm IC siren waveform there. And then now I've introduced the space-4's IC bomb drop effect. And of course I can use the press switch to also interlace some other potential sounds over it. Somebody's calling my phone. So that's how Project PC71 works. And now we're going to look at Project PC72, which is the space-4 music combo PC. So here at Project PC72, the space-4 music combo PC. There it is in the book, and here it is on our board. So we have our music IC, which is going into our speaker and 2.5 3-volt lamp, just like the previous project. And of course we got our space-4 IC, which is also feeding into it there, being controlled via our press switch and photoresistor. And of course our whole circuit's turned on and off by our slide switch. So let me get the scoop going. So with the previous project, we were having the alarm IC's output continuously going to the speaker and the lamp, with the space-4 IC's output being mixed in with that. In the case of this, we got the music IC's music being looped over and over going to the speaker and lamp, with our space-4 being mixed in with it. So we'll have a little bit of a different waveform compared to the alarm IC. So we turn our circuit on, and we get our alarm IC output there, and we can see the playback there through our oscilloscope on the waveform. Of course, I can take the space-4 IC out of it and just get the music IC by itself. And if I let the space-4 in there, we can of course see the space-4 IC's effect of it being mixed in with the music IC. I'm just changing the audio effects here. Again, making the space-4 IC cycle through different sounds here just with the photoresistor. So the music IC's waveform is still pretty constant. Basically, the space-4 IC is being overlaid on there in the little bumps and bits that you see here. So that's pretty much how Project PC72 works. So now for the very last project, Project PC73, the Sound Mixer PC. So here it is, Project PC73, the Sound Mixer PC. There it is in the book, and here it is on our board. So, like the previous projects, this time we have our music IC and our alarm IC. Both are being fed into our speaker and 2.5 3-volt lamp output there and being mixed together. So they play constantly. There's nothing like the space-4 IC where we can change the sounds. They're both going to play the exact same thing over and over and just get mixed at the speaker and light there. So let's get Cam Studio and a scope going. And we simply just power on the circuit. And so we can see on our waveform here, we can see the alarm IC and music IC being mixed in there. So if I take one output out, you can see the one output of our alarm IC there. And if I take that out, then you can see just the waveform of the music IC on there. And then when we mix them together, now you can see the difference. So we've got the waveform here, the music IC, occasionally being interfered by the alarm IC's output being mixed in with it, which is kind of getting all these effects on it. What they look like on this. We can see some effect there on 5 milliseconds per division. So, that is it. That is project PC73. And that is the last project of the PC CI-73 system here from Snap Circuits. And it is the last project of the entire Snap Circuits system.